annual compounding, which happens once a year, semi-annual, which happens twice a year, quarterly, monthly, daily. You can have compounding every hour, every minute, every second. Or you can have compounding that is happening constantly, like the calculations are just continuously being calculated constantly. It's an infinite number of calculations. So it's infinite compounding. And we have a formula for continuous compounding, and that is B is equal to PE to the RT. And E is a mathematical constant. And it is the base of the natural logarithms, but you guys don't really need to know that. You just need to know that it's a mathematical constant, and E is approximately equal to 2.71828, and then it continues. We will use 2.718, kind of like in pi. With pi, you use 3.14. With E, you use 2.718. Okay. So to calculate this, we're going to have $1,000 times E at 100% interest. So 100%, if I turn that into a decimal, is just 1.0. So 1 times T, which is 1. So that would be 1,000 times 2.718 to the 1, which is just 2.718. So that would be 2718. Now, there's a button on your scientific calculator. Let me pull it up real quick. Okay, so let's see a kind of a more realistic scenario. Bank accounts, that last example had 100% interest rate. That will never happen, ever. 4.3% interest. When our textbook was being written, it was written before the crash, and interest rates were higher then. We didn't talk about that. I know there was the question as to whether a bank could have a radically different interest rate, and I said no. And that is because interest rates are dictated by the Federal Reserve Bank. You guys have heard that, the Fed, on the news, like the Fed is talking about raising or lowering interest rates. They control how interest rates work. And the way they do that is the Federal Reserve Bank loans money or puts money out to the different banks. And they set that interest rate. And then the banks base their interest rates on that interest rate. And so right now, interest rates are very low, which is good if you want to borrow. But it's bad if you're trying to save money and earn interest. It's kind of a double-edged sword. Like when interest rates are high, you earn more interest on your money, and that's great, but then you also pay higher interest on any loans you take out. When interest rates are low, it's good to borrow money, but you don't earn anything on your savings accounts. And right now, interest rates are very low. And that's why all the banks are really low. But back when this book was written, 4.3 was pretty average savings account interest rate. And eventually they'll get higher again. So, okay, so we've got $1,000 E. Our interest rate is 0.043, and our time is 5 years. Okay, so we want to multiply that 0.043 and the 5 first. And so I have 1,000 times 2.718 to the 0.215. And then next I want to do this part. So I I do e to the 0.215, and I get 1,000 times 1.239861,897, etc. And at the end of 5 years, I will have $1,239.86. So let's compare that to daily compounding. Okay. Let's compare this to daily, because it seems like if you're talking like infinite compounding, seems like it would grow money like crazy, right? Doesn't it? Like you're compounding like every microsecond, compounding interest, compounding interest, compounding interest. So let's compare it to daily to see what it would really be. So if we did the same deposit, same account, interest rate, same amount of time, but daily compounding. So we're going to use our compound interest formula. So 1,000.043 divided by 365 to the 365 times 5. And again, I'm going to do this part and this part. Okay, and then I'll take and add that and raise it to the 1825. And I'll get 1,000 times 1.239846196. Is that what you would have expected? It's a 2 cents difference over 5 years. And like intuitively, you would think if you're compounding like infinitely, it would grow the interest like, so much more. But the reality is every time that compound interest happens, you're talking about micro fractions of pennies that are being earned. Because the compounding is happening so much, it's never like even a whole penny. And so in 5 years, you earn 2 pennies. All right, so we talked about compound interest formula, and that's what we did yesterday. And it's useful enough, but it's not terribly realistic, because compound interest formula only works if you take a chunk of money, say $5,000, and you stick it in a bank account, and you never touch it for 10 years. And then it'll tell you how much you have at the end of that 10 years. But most people don't save up money that way. They don't take some big chunk of $5,000 and stick it in the bank and then leave it for 10 years. Most people budget savings, and so they put away a set amount every month. Maybe they budget to put $100 into savings, and so they put $100 into the account every single month, and it builds. That's more realistic. Now, granted that some people can't put the same set amount in every month. Maybe one month it's 100, maybe another month it's 90, maybe another month it's 120. But you can say you put in about $100 a month, and you can use this for goal setting. Like to know, if I put away $100 a month for 5 years into this bank account, how much money will I have? that's a more realistic scenario, and it requires a more complex formula. So future value of a single deposit, it's a little wide. Single deposit investment. This is one-time deposit. That's still a little wide. Oh my goodness, what did I do? Okay, that's a one-time deposit. You never put any more money in the account. That uses the compound interest formula. So B equals P times 1 plus R over N to the NT. Okay. Future value of periodic investments. Okay. Future value, meaning how much money will I have if I deposit X amount of money for some number Y of years. Okay, this tells you how much money you will have later. And this means you know this, you know the deposit, and you know for how long. And then you're going to find the balance. Okay. And that uses this formula. And all of these letters all stand for the same thing they've all already stood for. This is the compound interest formula right here. And we added a -1 and an R over N to it because that accounts for the monthly. Now the difference here is this principal. This is your periodic deposit. Why? Okay, so this is the amount that you're going to put away every week, every 2 weeks, every month. Okay. The one thing on this, the number or the frequency of the deposit, I should say, the frequency of the deposit has to match N for the formula to work. So if it's monthly compounding, you have to talk about a monthly deposit. If it's a weekly compounding, you have to talk about a weekly deposit. Even if you were only going to put the money in once a month, you'd have to divide it by 4 and calculate the weekly amount. Actually, you wouldn't do it that way. You'd multiply it by 12 and divide it by 52 to calculate the weekly amount. Okay. Then you have your R. Again, rate as a decimal. N and N. Oh, it's the green that doesn't show up. It's the number of times compounded per year. And finally, T is time in years. And 1 is just 1, both times. All right, so Rich and Laura are 45, and they're going to open this account at Rhinebeck, and they're going to try to retire by age 65. So that is 20 years. They're going to deposit $5,000 a year into an account that pays 4.5% interest compounded annually. So your deposit is once a year, your compounding is once a year, so they match. You just want to check that and make sure they match, and if they don't match, you want to fix the deposit to match the compounding. Okay. So we'll take our formula. And we're going to plug stuff in. Our deposit is $5,000. Our rate is 0.045. We're compounding annually for 20 years. Okay. I'm going to multiply 1 times 20, and I'm going to divide 0.045 by 1. And I'm going to amaze you with my mathematical abilities because I'm going to do it in my head. Oh, see? It's impressive. I'm going to multiply and divide by 1. See? Ta-da! In my head. No calculator needed. Okay, I will use a calculator for this next part though. I'm going to go ahead and add that and raise it to the power of 20. So it's going to be 1.045 raised to the power of 20. And that's going to give me 2.411714025 minus 1 over 0.045. Then I'm going to go ahead and subtract that. Which is going to be 1.4117, etc. divided by 0.045. Then I'm going to multiply those. And I'm going to get 705857024 divided by 0.045. So I'm going to divide. And when they retire, they will have $156,857.11. And just to talk about comparisons, they're putting away $5,000 a year for 20 years, so they will have actually deposited $100,000. Just write a little note off of that. Okay, so they're earning almost half of their money, or oh, sorry, a little over half of their money in interest, right? Because 56,000 is more than half of 100,000, so that's pretty good. Any questions on that first part? Okay, when it asks how much interest will they earn, I kind of skipped ahead. We have to find the actual deposited money, which equaled the 5,000 times the 20 years. So $100,000. And then we take the balance and we subtract the initial 100,000. And so they will have earned $56,857.11. Let's talk about Linda and Rob some more. Wait, that was Rich and Laura. Sorry, Linda and Rob. They're opening an online savings account that has a 3.6% annual interest rate compounded monthly. And they're going to deposit $1,200 a month, and we're going to find out how much is in the account in 10 years. So we're going to use our formula. Can you guys believe I have that thing memorized? I use it enough. Oh, is it really? That's funny. So compounding monthly is 12 times a year. So we're going to do 12 times a year for 10 years. Okay, again, I'm going to multiply that and divide these. Today my pen is weird. Okay, so I'm going to get 1,200 times, I'm just going to go ahead and add them. 12 times 10 is 120. I'm going to raise 1.03 to the power of 120. So I have 1,200 times 1.432557169 minus 1. And I'm going to subtract 1. And then I'm going to multiply by 1,200. And then divide. Okay, so if you put $1,200 a month at a 3.6% interest rate, you will have $173,022.87 at the end of 10 years. Figuring out going one direction, I put away so much money right now, and that means I'll have so much money in 10 years is great, because you can figure out how much money you'll have in 10 years. But if you're talking about goal setting, I want to buy this thing in 5 years, whatever that thing is, and it costs this much money. How much do I have to put away now to have that amount of money in 5 years? This is a really practical, relevant, realistic application. People need to save up money to have a down payment for a house, to have money for a vacation, to have money for a Christmas fund, to have money for a wedding or a car. You want to buy a car outright in 5 years and you don't want to finance it. How much money do you have to put away every month? You know, this is for planning, for goal setting. And we have, again, sort of the more unrealistic. This is a single deposit. Okay, so present value, we had future value, which is how much money will we have later. Present value is how much money do I have to put away now. Okay, so you know how much you want later. Like, you know the later, you want to know the now. On the other formula, you know the now, we find out the later. Does that make sense? Okay, so present value of a single deposit investment is how much to put in the bank today and not touch to reach the goal. And then the present value of a periodic deposit is how much to put in the bank every, day, week, month, etc. You can figure that out to reach the goal. Okay. The present value of a single deposit investment, again, single deposits are not typically very realistic. This is not what people tend to do. I don't say, okay, well, I want $20,000 for a brand new car in 5 years, so I need to put $16,000 in the bank today. Because that's kind of how that turns out. And it's not very realistic. But to figure out, I need to put, $275 in the bank every month is sort of a more realistic thing. So this is the single deposit. It's not the more realistic, but this is the goal. So it's the balance in the account at the end. That's your goal amount. This is your single deposit. I guess that's already there. And then rate, and then number of times compounded, that's the same. And then finally we have T, which is the number of years. Mr. and Mrs. Johnson know that in 6 years, their daughter Anne is going to need $20,000 for the first year of tuition. So they want to know how much to put in the account today, one deposit, to reach that goal. Okay, so this is the goal. So they want $20,000. They're 5% interest, and it's going to compound annually. And it's going to be in 6 years. And again, I'm going to divide and multiply in my head and be amazing. And then I'm going to add in my head and be amazing. Oops. There shouldn't be two equal signs. I don't know why I did that. Okay. Then I have 1.05 to the power of 6. I'm going to divide 20,000 by that. And today they're going to have to put $14,924.31 in the bank. Oh, round to the nearest thousand. Sorry, I didn't read my problem. You should always read the problem. Round to the nearest thousand. So they have to put $15,000 in the bank today to have $20,000 in 6 years. So do you see why I say this scenario is not terribly realistic? Right, to stick in the bank and not touch for 6 years. It's not generally very realistic. The periodic deposit ones are much more realistic. Another single deposit. Now, here's how you can tell if you need to use the single deposit or the periodic deposit. It says, how much must she deposit in an account? It doesn't say how much must she deposit every month, every week. Do you see the difference? So if it's using the other formula, it'll say how much must she deposit every however so often into an account. So this is going to use the same formula. And she wants $100,000 in 10 years. She's compounding daily. So we've got that happening. So we have $100,000. And I'm going to divide 0.038 by 365 and add it to 1. Okay, that's 5. That's sort of hard to see. Okay, then I'm going to raise that number to the power of 3650. And I'm going to divide $100,000 by that. And we're going to round it to the nearest dollar. So she would have to have $68,387, and this is really unrealistic because it says she just graduated from college. She still probably doesn't have $68,000 if she just graduated from college. She probably owes $68,000. I'm just saying, it's not terribly likely, but again, these single deposits are not terribly realistic for most people. Any questions? Okay, here we go. Here's a very realistic scenario. Air conditioning units have sort of a life expectancy. When you buy it, that you can find, it's in the instructions or something, the life expectancy of the air conditioner unit. Most of them are probably 10 to 20 years, depending on how cheap it was. And so you know ahead of time, okay, this is probably going to be coming up due soon, that I have to replace my air conditioner. So Nick is going to install central air conditioning in 3 years, and it's going to cost $15,000. How much must he deposit monthly into an account that pays 4% interest compounded monthly? So those match, which they need to, and we want to figure out how much to deposit every month to meet that goal. So this is the formula that you use, so the periodic deposit formula. Okay, so we added an RN to the top and a -1 to the bottom. Okay, so he wants $15,000. His rate is 4%. It's happening every month. In 3 years. Okay, so first I'm going to divide this and multiply that. It's repeating 3's, by the way. Okay. Next, I am going to multiply this for my numerator, and I'm going to raise this to the power of 36 for my denominator. Then I subtract 1. And then I divide 50 by that answer. Whoa. And I get 392.86, but we want to round it to the nearest hundred, so he needs to put away $400 per month.